Cataclastic flow. We talked about this in a fault where the fractured rock is grinding and rolling to help the fault move more easily. And the same thing can happen in a rock that isn't actually faulting. It's just the grains and or sediment, the grains or crystals in the rock rolling and moving past each other. Think of like a big bag of marbles. You can have different size marbles, different composition marbles, doesn't matter. You start applying a vertical pressure on that bag, the marbles slide and roll past each other, and your bag deforms from something like A to something like B. Now, as long as you don't push too rapidly or too hard, each individual marble stays perfectly fine and safe, and the only deformation is this cataclastic flow. If you push too fast or too hard, you may fracture some of the grains, and then you get something like down in C at the bottom of the screen here, where then you have fracturing and sliding on the plane of fracture, so basically a super micro fault at the grain size. And the rest of it is cataclastic. Now, an important feature of this cataclastic flow is that there's no strain localization. There's no point in the rock that's straining the most. There's no point in the rock that has higher strain than the other. The grains are freely moving past each other and relieving the stress that way. You can see here a real-life rock under the microscope, and the top half of this is quartz, and the bottom half is potassium feldspar, and you can see that the potassium feldspar crystal has been broken, and where it's contacting the quartz and feldspar are contacting, the pieces of feldspar are kind of breaking off and rolling and moving past each other to relieve the stress of that quartz being moved across the edge of the feldspar. Now, crystal defects. This is the next section in the chapter. A crystal lattice can allow motion which results in ductile behavior if the lattice is imperfect. Now, an ideal lattice, like a halite crystal, for example, is sodium chloride, has a nice, rigid, perfect pattern of alternating sodiums and chlorines. If the crystal is perfect, it makes a nice cube, and there's no real way to have any kind of ductile behavior. All that's going to happen is brittle deformation. You stress it and it's either going to stay fine or it's going to break into smaller cubes and you have brittle deformation. But if there's an impurity or an imperfection in that crystal lattice, this can lead to ductile deformation. Now, there are three types of imperfections or defects. There's a point defect, a line defect, also known as a dislocation, and there are planar defects. So 0 dimensions, 1 dimension, and 2 dimensions. The point defects come in a couple of flavors or types. There's a vacancy, so we have this nice regular crystal lattice of these white circles, regularly spaced, all the same size, and then there's one missing. So there's a vacancy here. That's an imperfection in the crystal. On the other hand, so is this gray circle that's a little bigger than the white ones. It's substituting in. It's taking the place of a white one. A substitution, which is a substitutional impurity, can be a different atom or ion that's a little bigger or a little smaller. In either case, it's going to stress and strain the matrix of that crystal around it. The other kind of impurity is called an interstitial impurity. And it's like this little black atom that's been captured or trapped inside the crystal matrix. So it's not taking the place of any of these little white circles. It's just trapped. It's stuck there. So those are the three types of point defects: a vacancy, a substitutional impurity, and an interstitial impurity. The vacancies are special because they can move. If you have a vacancy, and obviously all around that vacancy are atoms or ions, which is just a charged atom, one of those atoms can move and fill that vacancy. If that happens, there's now a vacancy where that atom came from. So if this white circle that has an arrow on it moves down to the right and fills that vacancy, there will now be a vacancy right where that atom came from. So the vacancy isn't going away. The vacancy is moving when the atoms move. The vacancy is moving in the opposite direction of the atom. That's important. You'll see why on the next slide here. Vacancy migration. Notice we're not talking about atom or ion migration, we're talking about vacancy migration. Vacancies move based on concentration gradients. So it could be, we think of concentration being like how concentrated is the salt in the salt water, but it can also be the atoms in the solid. Now, material, like atoms, moves away from highest stress. If you have a blob of Play-Doh and you push downward, it moves away from your hand and bulges out to the side. That's easy, that's logical. We can wrap our brains around that pretty nicely. When you have a solid, however, unlike the Play-Doh, it's not just squishing out of the way. You have that pressure pushing down. The object stays looking to the from the outside exactly the same. But internally, some of those atoms are moving down and away from that highest stress and filling in vacancies. That means those vacancies are now where those atoms used to be. The vacancies moved towards the highest stress. Again, we'll see this even more later, but this is important. That's why I'm reiterating and kind of breaking it down. So whatever source of high stress you have, the atoms move away from it and the vacancies move towards it. The substitutional and interstitial impurities don't really migrate. The only way they possibly can is if they're moving to fill in a vacancy. And again, then it's the vacancy migrating in the opposite direction. But it's important to note that both the substitutional and interstitial impurities are weak points in the crystal structure. They're straining the bonds between each ion, between each atom.